Good evening, everybody. I'm Dave Rothery at the Open University in the Open STEM Labs. I'm the chair of S283, that's our Level 2 Planetary Science course, and I'm the lead educator on the Open University FutureLearn Moons MOOC. So whichever of those you're studying, or even if you're not studying with us, welcome. And we're going to talk about some news and then answer your questions. I'm very pleased to have with me my colleague, Hannah Sargeant. Good evening, Hannah.
Good evening. Hi, everybody.
It's nice to see you here. We'll find out a little bit more about Hannah very soon. Let me just mention, though, we've got 3 widgets if you're watching live. We'd like to know where you are. But also we've got a couple of polls here. We can perhaps see one of them. What's your first choice destination for the next lander? And then there's another one, after that, where would you put the next lander after that? Or what's your second choice for the next lander, basically, just to see where people think we should be sending landers to. We'll have a look at those widgets at the end. I see Europa's way ahead there at the moment, but we'll see how it looks at the end. Okay, well, I brought Hannah here for a reason. Hannah, you've got some pots of stuff there. Tell us what you do, because you're a postdoc here at the OU now, aren't you?
Yeah, that's right. So I finished my PhD with the Open University last year, and I've since been continuing to work within sort of that similar team, working on things related to resources on the moon. So that's what I'm really passionate about, is finding water in particular on the moon, and then using that to support future missions. That's because water can be used to keep crews alive, but it can also be used as a resource for propellant. So the hydrogen and oxygen in H2O can be rocket propellant. So first of all, why do we think there's water on the moon? Because it looks pretty dull, in the sky, this ball of rock. But there's recent evidence in the last few years that's telling us that there's water in the polar regions of the moon. And this is because the axial tilt of the moon isn't actually that much. It's a very small tilt, which means that it's spinning like this, and as the sun is coming in from one side, there are craters in the North and South Pole which never see sunlight, and they're extremely dark and extremely cold. And because of that, if water ever is brought to the moon and it hits those surfaces, it will stick there. So we think that this is collecting over really long periods of time.
In fact, people on the FutureLearn Moons MOOC will learn about these permanently shadowed craters with the cold trapped water ice in week 6, I think it is.
Yeah, it's a really hot topic, especially right now. It's why we think there might be some, we want to target moon bases to go to these regions. But I'm interested in all sources of water on the moon. So it's great that there could be water in the poles, but we might not always want to land at the poles. Yeah. So I'm interested in looking at how to get water from just the dry rocks itself, and you can do that with chemistry. So what we have here, we have some lunar simulant. So this is what I've been testing my experiments on, and this is effectively like mock lunar soil, and it's based off of the minerals that we know are found on the moon.
Is that the actual grain size of lunar regolith?
Yeah,
it looks pretty fine.
It is, and that's because we want it to match as close as possible to the properties that we'll find on the moon. So we've matched as well. The team who developed this simulant has matched the grain size as best they can and the minerals. And what we've been doing is practicing an experiment that we plan to do with PROSPER, which is an instrument developed at the OU. Which will hopefully try and heat up some lunar samples with some hydrogen, and that hydrogen will bond to the oxygen in these minerals and produce our water. But it won't react with all of the minerals that we find there. It will only react with certain minerals, at least with this reaction anyway. So I'm interested in ilmenite. So this is it's an iron-rich material.
Iron titanium oxide.
That's it. That's right. And so this mineral here is extremely dark. That's because it's got this it's very rich in iron. And so if you do look up at the moon and you see there are darker shades and lighter shades of material there, those darker areas, which are the mare, are rich in this material. So if we didn't want to go to the poles, perhaps we could go to a mare region and look at this reaction.
So you pass hydrogen over heated ilmenite, and it turns into the oxygen bonds with it and turns into H2O.
Yeah, that's the plan.
So to make your water on the moon, you have to bring hydrogen with you from the Earth, or are there ways of finding hydrogen on the moon to add to the ilmenite
Yeah, good question. The answer is you can do either. So we'll be in our test with Prosper, we'll be bringing hydrogen with us. It's kind of part of the reason why we quite liked this experiment, because it's maximising what was already flying to the moon anyway. But because hydrogen's so light, it's okay if we do launch it from Earth. But if we wanted to, there will be hydrogen, which is this solar wind implanted protons, which is what hydrogen is, just covering the surface, and we can possibly extract that to do this experiment.
So you could live off the land through your reaction if you can't go to the poles and find ice there.
Yeah, there are absolutely there are other ways, and in fact, what I've been doing, it's not necessarily the most efficient, but it's a really nice one to test early on. But there's like 20 different ways of extracting these materials.
That's great. Thank you.
So enough about me. Some of the viewers might know that you've been involved in some of the current Mercury mission.
Yep.
And they might have some questions about that coming up, hopefully. But is there anything else that's caught your attention in the recent news?
Well, I mean, the news I want to talk about would have been fairly obvious last week. I mean, we've got another big news story coming up that Hannah's going to talk about. But what I'm going to talk about is the Perseverance landing on Mars. I mean, wasn't that an absolutely wonderful landing? A lot of you will have seen the video of it. It's a very capable lander, and it's been put down on a dry lake bed at the front of a delta. It may be 3 billion years old, but there should be well-preserved record of this deltaic sedimentation coming in, and there may well have been an environment where life could have occurred. So Perseverance is going to be looking for signs of life. Let's have a look at the pictures. The first one's an oblique view. It's a synthetic view, looking down on the delta. So what you're seeing there is a ancient river channel coming out from the highlands, which are the terrain beyond the impact crater. The lower ground in the foreground is on the floor of the crater, and you can see the front of the delta. That's the prominent landform in the middle. And for scale, the biggest crater on the top of the delta is almost 1 kilometre across. This is a crater that's formed after the delta was active. And the lander actually put down in the lower left of that view, just above the word image credits, is where the lander landed, which is pretty much exactly where they wanted it to go. There was a video released. It landed on the Friday night, didn't it? But by Monday evening, there was a video released that the lander had took on its way down through Mars's atmosphere. I've captured some still frames from the video, so let's take a look at that. And the first one will show you the front of the delta. Maybe you'll recognise that delta front. It's rotated about 90 degrees from the previous view. This is the downward-looking camera on the lander as it went down. And this was being carried down on, with a sky crane rocket above it, which you'll see come into play later on, and a parachute above that. So let's just follow it down to the surface. When you look at there's the actual landing site come in view. That X marks the spot. I put that in to show where it was going to land. When you watch the video, it's kind of hard to keep track of because it is swaying underneath the parachute and things keep coming in and out of view. But if we follow ourselves down, you can try and keep track of what's going on. We lose sight of the delta now. But
what's quite interesting with this, I found, was that how accurate they were able to land, which is, most times sort of the landing area you're expecting is, tens of kilometres wide, whereas this was very accurate.
It was a big landing ellipse, many tens of kilometres long and rather narrow, but they steered it brilliantly. They were steering it before the parachute deployed, and I think after the parachute deployed as well, they landed somewhere safely. We're beginning to see rocks come into view. I think the next view, you'll see the ground disturbed as the sky crane rockets turn on. You'll see dust being blown. So one more view before we hit the surface. There you go. So you see that the swirls of dust there, but they're being kicked up by the exhaust from the sky crane, which was above the lander. And then the sky crane cut loose and the lander hit the surface. And we've got a view from orbit at almost this same instant. There you go. That's a high-rise camera view from an orbiter. And the coloured thing in the upper right is the parachute, which looks distorted. Well, it is, because they've just cut it loose and it's deflating and being detached. And that white blob is the combined lander and sky crane. You might just see radiating away those flares of dust, which are the rocket exhaust, hitting the ground. And then it touched down. It was a brilliant soft touchdown, somewhere very safe. Let's see it on the surface. That's the view from the surface. And it's looking towards the north, towards the delta. The very distant mountains of the rim of the crater, that plateau in the middle distance, that's the top of the delta. And it's sitting on this now dried out lake bed with various rocks scattered around. Some are dark, some are light. Let's have a close-up view of one of these rocks. Okay, so there's one of the lander wheels, and there's rocks there. These are all pretty much the same looking kind of rock in this view, but I mean...
What is it that's interesting in particular, or that caught a lot of attention of those scientists seeing those first images? It's the holes in those rocks.
Those rocks have holes. Now, they've not yet been analysed. We don't know what they are. One possibility is they're lumps of lava, which have been dispersed, thrown out of impact craters into this area. But they've got holes which would be gas bubbles, because when lava erupts, gases come out of solution and form bubbles. Let's have a look. I've got a sample of rock here. If we can turn onto this view here. Here's a piece of volcanic rock from the Earth, and you see there are bubbles all over it, gas that's come out of solution. Is that what we're seeing on the surface of Mars? Could be. We don't know yet. I mean, it doesn't have to be gas bubbles. It could be clay that's settled on the floor of the ocean, or the lake bed rather, not ocean, and that's had minerals growing within it as the lake evaporated. Evaporite minerals like gypsum, for example. And those gypsum crystals have now gone because they've been plucked out by the abrasive Martian wind, leaving those holes behind. So are they vacancies where crystals used to be, or are they original gas bubbles, or is it something else? We don't know, but we're going to find out. And then the rover is going to make its way towards the front of the delta, and it will climb up the delta eventually. I hope it doesn't rush this, and I'm sure it won't. There's a lot to see on this dry lake bed before we start investigating the delta, and eventually go onto the river channel that fed the delta. It's going to be a marvellous mission.
So how does this mission compare to all of those others that have been sort of sent to Mars?
Well, it's the most capable one. It's got lasers for going pew-pew at the rocks and analysing what's in them. It's also going to be collecting samples to cache them for a future sample return mission. But let's not forget there's still one excellent rover that's still doing a grand job on Mars. Go back to the next slide, because our attention has been taken away from Curiosity by this wonderful Perseverance
The phenomenal
lander.
Curiosity.
But Curiosity has been blooming brilliant. That had a very good landing on a former lake bed, but mostly covered by river deposits inside Gale Crater. And it's been going for many, many years, and it's in a long traverse. Let's just see where Curiosity put down. So the marker there is the pin where it landed. You can see most of the crater it landed in, and a very large erosional massif in the middle called Mount Sharp. And if we look at the final picture, you can see the traverse. That's between 25 and 30 kilometres that rover has traversed over. It's getting on for 10 years now. It's done a marvellous job. It's come off the lake bed with lake sediments and evaporite minerals and stuff deposited by flowing water. It's now higher in the sequence, where the rocks were laid down by the wind. These wonderful large-scale dune cross beddings, which really attract a geologist like me. So that is a great mission too. And if Perseverance lasts as long as Curiosity, it will very easily cover the lake bed and the front of the delta and the top of the delta and the river channel. It doesn't have to do a traverse that long to cover what it needs to do. So that is going to be a brilliant mission, because they've landed so well.
Yeah.
So I'm really
Many great things to come.
Absolutely, there are great things to come. So that was a news story I brought along. Now, Hannah, what news story do you want to talk about?
The biggest news story of the day. This, so the Witchcrumb Carbonaceouschondrite, the meteorite that was found that fell in the UK just over a week ago, and some of those fragments have been found. And this is thanks to a great effort by a bunch of researchers in the UK who've been trying to increase our observations of meteorites as they're falling, to try and triangulate where they land. And they've been able to find exactly kind of the rough area. They put out.
They did it very well.
They did a very good job, and they managed to put out a call to people on the news to say, look, this is, we think it's going to be roughly here. This is how to safely handle it so that they could keep it as preserved as possible, not damaged by the environment or by anyone picking it up. And a very gracious family has donated that sample. Well, they thought they found a sample, and one of our researchers here, Dr. Richard Greenwood, went over and took a look at the sample, and he said his legs went jelly, and he got almost a bit emotional as he took a look and saw this is incredibly rare meteorite, because it's a meteorite. We think it's a carbonaceous chondrite. It's this we've got some images of the sample that was collected. It's incredibly dark material, as this is very carbon rich, and they think it's this primitive material from the early solar system as planets and things were starting to form and coalesce. And you might notice those are the white spots. Would you tell us a bit more about those?
Yeah, well, we've got the fusion crust. That's the outside surface which was melted by the heat that's developed by compressing the atmosphere in front of the meteorites. You've got the melted fusion crust on the outside that's cracking, and there's one light-coloured blob. But if we look at the next picture, it's broken open, and you see inside the chondrules. So that's got these features which are a millimetre or so in size, which are these globules that form within the solar nebula, and they may have crystalline minerals in them. But the black stuff is a really carbon-rich matrix, and which is a really primitive, not altered.
Absolutely, it's just this really loose material that sort of came together in the ancient solar system, and it's eventually found its way to us. And what's quite exciting is that often these samples have very high water content, and they don't last very long when they hit the surface. So it was only by collecting it and preserving it so quickly that they were able to save it. And it's going to be a really great example of the samples that we want to collect, or that are already on the way back from other asteroids like Bennu. And hopefully some analyses that we hope to do would say this meteorite will then be applied to these other collected samples. And so some of these samples have already made it back to the OU. There was a bit of a relay going on to get those samples, and some of them into the lab. I think there was one exchange.
Here we go.
Yeah. Oh yeah. Here's Richard on the left. Collecting one of these samples, and then as well as on its way to the OU, there was an exchange in a Tesco car park as the researchers were getting these around the country. And on the right, we have a fellow PhD student, Ross Finley. I've been working with him in the office. He's been keeping it quite hush until this morning, and that's him actually performing these isotope measurements. So trying to understand what the ratio is of the different types of oxygen that you can find. So you can have oxygen of different masses, and by looking at those ratios, you can figure out whereabouts in the solar system it will have formed. And that's what gives us this clue that it's a carbonaceous chondrite.
Yeah, and then we're going to be looking at all the organic molecules and see whether meteorites like this could have seeded the Earth with organics.
Absolutely, the building blocks of life are these organic materials. So, so it could be a really exciting project.
It's really good to have got a carbonaceous chondrite within 12 hours of it hitting the ground, because it's not been weathered or contaminated, and it's a sizable sample. There's 300 grams.
I put something of that scale, and
it's about half a brick's worth.
And the fact that they've all been collected and some have gone to analysis, I think it's potentially like the fastest any meteorite has gone from falling in the sky to being in a lab and being studied.
Yeah, this tracking network triangulating the fireballs on the way and really proved its worth. Yeah. I saw the map of predicting where it was going to be across the Cotswolds, and they got it right.
Absolutely. Okay, so let's have a look at some questions.
Yeah, well, I've got one for you, really, Hannah. On the Moon's MOOC, Kate Warburton has asked, what's the latest on plans to revisit the Moon with crewed spacecraft?
Well, apart from this slight distraction with Mars and some meteorites, the Moon is basically all there is in space exploration in my world. So there's a huge drive to get humans on the Moon, but this time it's not just for a short stay and returning home again. Now we're really talking about these longer duration missions. So we've got teams, massive international teams. So you might have heard of the Artemis program, which is this idea of building a lunar base and an orbiting station. And there are other projects from other nations as well. So we're thinking it's probably going to be a lunar polar base, again, looking for the water and actually you can get more on the tops of craters in the poles. You can get near permanent sunlight, which is a great appeal for a base which needs power. So hopefully we'll be having crews on, or boots on the moon, as they say, sometime this decade is the plan. Is this just NASA, or is the European Space Agency in partnership with them? So European Space Agency are involved. So I think there's an agreement to, at least because ESA are collaborating with this orbiting station. And as part of that, I think there is communication going on with regards to getting an ESA astronaut in orbit around the moon. I think Canada are going as well, and there's just going to be a lot of nations collaborating for this end goal of boots on the moon. Yeah, but let's not forget the Chinese, because they've done uncrewed sample return from a part of a lunar near side which had not previously been visited, Oceanus Procellarum, and they've got a lander, a rover, still operating on the lunar far side. It landed in January 2020. It's done it's done 13 months, 14 months now. Yeah. And that's not easy, because the lunar night, you have to survive 14 days of lunar night. And you can't communicate with the Earth unless you put a relay satellite in position. So they've done all that. And they're gearing up to put people down, aren't they? Absolutely. That sample return you mentioned, it was a really complex process to get that sample return. It doesn't have to be as complex as they made it. It's because they were preparing for getting humans on the moon and back again. It wasn't just simply just a rock collection exercise. So some very exciting things coming, that's for sure. Yeah, they've got quite a heavy lift capacity off the moon, haven't they? And they've tested it now. Yeah. So they could beat the NASA ESA effort. I wouldn't be surprised. I think it's going to be a really, I don't want to say space race, because I don't think it should be about the first. I think it just means that there's a lot going, and we're going to get a lot of results from all areas in the coming years. Absolutely. We've got another question here. This is one for you from the S283 forum from Ringo Massa. And they ask, Ringo. I understand that Mercury has several aspects that are puzzling. It has a very large core, possibly because a glancing impact removed most of its mantle and crust. Also, it has a high volatile content, considering the close proximity to the sun. Could it be that somehow the two are actually related? We think they probably are, Ringo. I think Ringo was among those who was watching the Geological Society Eurospace lecture I gave online about Mercury last week. You can find it online, just search for Eurospace Mercury and you'll find me. Yeah, Mercury has a very thin carapace of rock encompassing a very large for its size core. And we think most of the rock was stripped away in a sort of hit and run impact between Mercury and something else towards the end of the birth of the solar system. So it was a differentiated body, a planetary embryo. It hit another planetary embryo and was stripped of most of its rock. And if it began somewhere out near Mars and was on its way in towards the sun and hit the proto-Earth or the proto-Venus and lost its rock, the rock that survived, coming from further out from the sun than it is now, would be carrying a lot of volatiles. If it formed in situ so close to the sun, Ringo's right, you don't expect a lot of volatiles there. But if it's come from some way out inwards, the hit and run impact that stripped it of most of its rock could have left the surviving rock with enough volatiles to give it this remarkable history. That's Mercury behind you there, Hannah. And there are explosive volcanoes there, not active today, but that have blasted up through the basalts, leaving holes in the ground. And that wouldn't happen if there was not a lot of volatile stuff that could turn to gas. It's a volatile-rich planet close to the sun. We didn't expect it. And to me, it makes sense to link the loss of the rock leaving a large core and the volatile richness with the fact that it's travelled from further out from the sun to begin with. It's not done and dusted yet, but we'll know more when Bepi Colombo starts doing science in 2026. Something to look forward to, for sure. Absolutely. I was going to look for a question on the live chat here, and I don't see one yet. I've seen, is the lunar water ice for real in the Apple TV series For All Mankind? Unfortunately, okay. I've not seen that show, so I can't comment on what that looks like. I did. There was a paper at the Lunar and Planetary Science Conference not so long ago about the water ice in lunar craters, and it was entitled "Don't Drink the Water,"
because it would be horrible tasting, it would have methane and other nasties there. You'd want to purify it. It would taste foul, apparently.
Yeah, so just because, we're talking about water sort of freezing down in the poles, but actually there are lots of other volatiles that might collect there, like CO2 ice. When we say ice, we don't just mean water. There are lots of other things in there. So it's not as simple as just heating it up and having a drink. There'll be a few more steps, I think.
Absolutely. Andy Sharp is asking here about objects being captured by the gravity of the planets, but if they get too close, they're ripped apart. Is this as dramatic as it sounds? Okay. Andy, you're talking about things that get pulled apart by getting within the Roche limit of a planet. That's the distance from it at which the tidal force, which differs on the near side and the far side, becomes greater than the cohesive strength of the body. We've seen a body ripped apart by tides. There was a comet called Shoemaker-Levy 9, which went past close to Jupiter, got ripped apart, and then was caught in orbit, and then eventually the fragments came in and hit the planet. But that was pulled apart tidally. So I think it is fairly dramatic if an object gets within the Roche limit and is pulled apart. They say it will happen to Phobos, the nearest moon of Mars. It's slowly spiralling inwards and eventually will be ripped apart.
But not anytime soon.
Not anytime soon. I think it's got some millions or tens of millions of years to go. But once the body starts to rip apart, it rips apart. But tidal flexing that our moon gets from tides from the Earth, or Io gets from tides on Jupiter, is just bending them a little bit, heating them up, but coming nowhere close to pulling them apart.
Yeah. Okay, so let's take a look at some of these other questions that we had sent in earlier. So we have a question for you on the S283 forum from Simon Austin. Mercury is not tidally locked, but presumably would be if it were closer in. How much closer in would it need to be?
Well, Simon, Mercury, in fact, is tidally locked to the sun. You're probably thinking tidally locked so it keeps the same face to the sun as it goes round, rather like the moon does to the Earth. That's one rotation per orbit. But Mercury is tidally locked in a 2-to-3 ratio. It makes 3 rotations on its axis for every 2 orbits around the sun. And that is tides which do that. It works because Mercury's orbit is the least circular of all the planet's orbits. It's the most eccentric. So at every perihelion passage, it's got an opposite hemisphere facing the sun. The sun's gravity locks onto it. So it is tidally locked in a 3-to-2 resonance. How closer would it have to go in? Well, we don't know. But what we do think is that planets which are really close to their stars, like many of the exoplanets that have been discovered, the TRAPPIST-1 system, we've got exoplanets really close to their stars, and we think they are going to be tidally locked, such that they keep the same face to the star all the time. But it hasn't happened to Mercury. It's settled down into this 3-to-2 relationship, which is long-term stable, we think. We've got more questions coming in.
I'm struggling to
Amy,
mine.
If Mercury had collided with Venus or the Earth, what evidence would we look for on either of those planets to support it? Well, we wouldn't, Amy. It would be lost. We're talking giant collisions, or collisions between similar-sized planetary embryos is the final stage of planet building. And when I said the Mercury-forming object would have hit the proto-Earth or the proto-Venus, it doesn't have to be the last such big collision that the eventual Earth or Venus body experienced. If you have something that's half Earth mass and 1/3 Earth mass and they collide and merge, you get a totally new body forming. And if something like Mercury careens off that, it won't leave much record even in the isotopic signatures, and certainly no record geologically, because the body is going to have a molten outer layer, it'll have a magma ocean. So the effect of the Mercury progenitor hitting a progenitor of Venus or Earth isn't going to leave a trace on the larger body. So it's going to be hard to find such evidence. The evidence we will get will be from Mercury when we either return a sample from Mercury, and there's no prospect of that for quite a while yet. It's a very hard place to land. So let's take off from and come back to the Earth. But there could be meteorites from Mercury. We've got plenty of meteorites from the Moon and from Mars. is when a crater-forming impact happens on one of those bodies, some of the debris that's thrown out gets into space. Not much, but some, and some of that finds its way to the Earth. It's about 100 times more difficult to get an ejector fragment from Mercury to the Earth than it is to get from Moon to the Earth.
So how do you know that it's from Mercury, these meteorites?
How would we know? We haven't found one yet from Mercury, but what we'd look for would be something that's, well, we know Mercury's composition. It's very poor in iron. There's only about 1 or 2% iron at the surface. It's very high magnesium and medium silica basalt type rocks. And it's rich in volatiles. There's sulfur, there's chlorine, there's quite a lot of sodium, there's a high potassium thorium ratio. And it wouldn't be 4.5 billion years old like traditional common or garden meteorites are. Common or garden if you live in Gloucestershire. And it would not match the Moon, it would not match the Martian samples. So we would conclude this is probably from Mercury, and that would be a good clue for us. And we'd really love to look at the isotopes within it. Cobalt and nickel, for example, which might tell us the history of core formation within that body. So a Mercury meteorite would look strange, so we probably haven't got one in the collection yet. And it ought to stick out like a sore thumb.
Yeah.
And keep looking. I wish this one coming in had been a piece of Mercury, not a blooming Carbonaceouschondrite, but Carbonaceouschondrite's the second best thing to find.
Absolutely, and I think the first one in 30 years. I think we can't complain too much.
No, we're very lucky, and that tracking network worked really well.
So I don't have, I can't connect. So you're going to have to search for any questions that come in.
Okay, well let's take a question that we had in already. Okay, here's one on the Moon's MOOC from Alan C. This is a fun question. I'm glad we've got time to ask this. Alan says, if you could swap any of the planetary moons with our moon to enable it to be studied very closely and to easily send crewed missions to its surface, which moon would it be and why? And he has a supplementary question. Which moon would you swap with our moon to make ordinary people look up to the night sky with renewed interest? We'll both have a go at this.
So I think that second part of that question, which is something that would be a really fascinating view, I think Enceladus, which is a moon of Saturn, it's an icy moon, so it's got this icy crust, and then this liquid ocean, we believe, underneath. And there's a massive plume that's coming out from the base of Enceladus, and it actually contributes to one of the rings of Saturn. And it would just be phenomenal to see that view as close to Earth as it would be. But the problem is, by moving it out of its current location, you're going to lose loads of its properties. So, moving ice this close to the sun, a lot of that might vaporize or whatever else might happen. There's some complex tidal heating going on.
You'd lose the tidal heating, wouldn't you? If you take it out of Saturn's gravity field and take it out of resonance with, is it Dione, the moon that's in resonance with, it wouldn't be tidally heated, and you'd turn the plumes off straight away.
That's the problem,
and kill all the life that you're hoping to find in the internal ocean.
Yeah, perhaps.
It would be nice while it lasted, but it wouldn't last very long.
And it does also have these really cool, they call it the tiger stripes. It's like these stripes at the base of the moon, which I imagine would look quite striking from here on Earth. But what about you? What would you argue?
Well, I would want to bring Europa close, because I think that's an even more attractive world for finding life. It's also a bit bigger than our moon, whereas Enceladus is tiny. Yeah. You have to bring Enceladus quite close to look spectacular in the sky. But again, take Europa out of orbital resonance with Io and Ganymede, you turn off the tidal heating, which is the stuff that makes it interesting, because Io's got an internal ocean, and we think hydrothermal vents with hot rock in touching water and the internal ocean, a perfect environment for hydrothermal life. But same argument, you'd turn off the tidal heating. But for a spectacle, which was a supplementary question, I'd bring Io here, because Io's got dozens of active volcanoes. Even the part of the moon not lit up by the sun, you'd have little spots of red where volcanoes were erupting. But again, take it away from Jupiter's gravity field and out of orbital resonance with Europa, it's not going to be tidal heated anymore. So the volcanoes would turn off after a few tens or hundreds of thousands of years. But while it lasted, it would be a really spectacular object in the sky.
Okay.
I don't think the budget's run to that, though, so it's not going to happen anytime soon.
Let's see what else we have. Any more? Are there any more live questions coming in?
Okay, well, Ralph Brady is questioning the age that Richard Greenwood said about of the carbonaceous chondrite. He said it would be he didn't say 4,567 billion years old. It's 4.567 billion years. Yeah. 4,567 million years. That's the age of the solar system. Just over 4.5 billion years.
When things were just starting to form and join together.
It's very early, very primitive object. Now we haven't dated this sample yet. We've just got the oxygen isotope ratios and seen the fractionation line that it falls on and identified it optically as carbonaceous chondrite. Yeah. So, but I mean, all known carbonaceous chondrites have this age. So I think Richard's pretty safe to say 4.567 billion years old. Okay, more questions we had in advance. Please ask some more live questions. But there's this one here from an S283 student, Adam Mauler. Icy moons are said to reflect sunlight in every direction, or scatter it, indicating that the surface isn't a smooth ice layer, but granular fragments. He's saying, what do we know about the formation of ice in the absence of Earth-like atmospheres and extremely cold temperatures? We're not expecting smooth ice. It's not because of the temperature at which it forms, are we? It's more the exposed environment to space. Yeah, so
you're always going to have these micrometeorite impacts, which will cause this sort of call it gardening of like the surface. It happens on our moon. It will happen on most airless bodies, but also, for example, I was talking to PhD student Grace Richards, who's studying Enceladus. She was saying that these plumes that are released, they will form this sort of granular deposit on the surface as well, and then on other icy bodies there will be constant the motions going on with the crust moving in and out and forming and reforming. So I would never expect a perfectly smooth surface.
No, well, on Europa, the cracks that open and close tidally squeeze out slush, we think, which forms these ball of string ridges and groove structures. And when you get melt through of the ice to temporarily expose the ocean, that's going to boil away to space. So you'll have gas bubbles bursting over it before it freezes.
Yeah.
So you're not going to get a chance to form anything that's glassy smooth to begin with. But if you did, it would then get pulverized by meteorite impacts and get snowed on from the plumes. So it's no surprise you don't find shiny sheets of ice.
Yeah, they're very dynamic surfaces.
Yeah. Stephen Romanovsky's asking, could Mars and Earth orbit each other like Pluto and Charon and somehow support life on both planets? This is his terraforming idea. You want to bring... Okay, we've been talking about bringing other moons to start orbiting the Earth. Stephen wants to bring Mars here.
That is the sort of thing, that's some complex of orbital dynamics that I can't process in my mind. I think anything within the habitable zone has a chance of life, if there's water, if it's got just the right amount of heat. So it really depends on how that might work. It'd be interesting to see how two planets of that size orbiting around the sun might work.
I think if you brought Mars closer to the sun, it'd be an easier place to support more abundant life, but it's still got too little gravity to hang on to an atmosphere with great ease and no magnetic field.
Which is what
so the solar wind could erode the top of an atmosphere as well. And I'm not sure that putting it in orbit around the Earth would help Mars. You might tidally heat it a little bit, but that's warming the interior.
Yeah, it's that lack of atmosphere that is the real problem with Mars hosting life.
We think it's a bad idea, don't we?
Yeah, let's not try.
I don't think we'll do that.
Okay.
Clay Specht is asking me, am I planning on writing any more books soon? Well, we've got a new edition of the books for S283.
How many more editions?
Well, we've got a new impression of that. So this is a third edition, but there's a second impression of a third edition coming out with some updates in it. but we'll have to get rid of, the next time we update it, we'll have to get rid of the Barwell meteorite from Leicestershire on somebody's drive and replace it with the Winchcombe meteorite from Gloucester. But I gather that that's not the official name yet. It fell in Winchcombe. The biggest sample was found in Winchcombe.
Yes.
How do these things get their names?
So there is, I think it's like a meteorite naming panel. So although a lot of people are calling it the Winchcombe meteorite, it's not necessarily, I mean, it will likely end up being something like that or of the sort. But there will be an official panel that will sort of decide on the official name.
Yeah, but normally named after the nearest post office, at least in remote parts of the world.
Yeah. So you'll find, so for those who don't know, the general nomenclature for these sorts of things is meteorites are named after where they are found. It's not related to anything about its history, it's just where it happens to fall. Yeah.
So the famous Martian meteorites that were first recognised, Sargeantites, Shashinites and Naklites, Naklis somewhere in Egypt.
Yeah, that was the Martian.
Sargeant is India, and Chassini's in the Alps, I think.
Yeah, I'm not the meteorite expert. I've had a crash course in meteoritics today.
You should have been paying more attention.
So we've got. Let's see what other question we have in here. So if money and technology were no object, where would you send a mission to search for life, and what would it do there?
Well, yes, I forgot we don't have a page. I would go to Europa myself. I mean, Enceladus, you can fly through the plumes from the ocean and sample them for free without landing. But if money and technology were no object, I would go to Europa, which is a bigger body, and we've got water on top of tidally heated rock, much more energy to support chemosynthetic life powered by tidal heating. And I'd get a submersible, a robotic submarine into the ocean to go and sniff out these hydrothermal vents and see if we could find things living there.
Yeah, the key really is it's these subsurface oceans, because life as we know it requires this water, this liquid water. So the only other sort of realistic destination, I guess, that's on our minds for current life would be in these subsurface oceans, in our solar system at least.
Yeah, but I've said we go to Europa to look for life. You've got to pick somewhere different. Where would you send?
This is assuming I don't know much about beyond Mars. I'm more into the rocky planets, I'm afraid, so I can't comment on those. I guess it would just have to be again Enceladus. I think it's got a lot of interest there. But then again, if you're interested in evidence of ancient life, so that's why we're interested in going to Mars, because we know there was flowing water there, so there could have been life previously, and I think that's the most that's within reach in the coming years to access that sort of information.
Always comes back to looking for life, or where life is today, or where life used to be. Why aren't we interested in the physical world so much? The wonderful geological processes, the sand dunes, the river sediments, the volcanoes.
Look, this is something that I've actually been speaking to a few people about recently. Is what is it that drives us when it comes to like the instruments that we develop and the missions that we're interested in, and ultimately, it seems that the search for life and understanding our place is kind of is like the end goal, or getting humans to travel further is almost the end goal, and everything else in between is fascinating and interesting, but it's almost like as an addition to this ultimate search for other things.
Yeah, search for life is in the roadmap for almost any funding agency, whether it's NASA or funding agencies in the UK. Why do you want to do this solar system research? If it's not helping understand where life can exist or used to exist, you stand much less chance of getting funding. If it's just a good scientific question. Yeah,
find a way to incorporate the search for life into your question and you might get funded.
Yeah. Oh, David Sly says, let's hope a meteorite isn't discovered in Llanfairpwll, Gingingog, over Planty Siliogogog. I bet you thought I couldn't say that, David. Alan Cooper is pointing out that Venus has a total of 50% of the votes from the widgets. We'll look at the widgets before we stop. Is sending a lander there practical at present, a lander to Venus?
So, I mean, it has been done. It was done a very long time ago.
True.
So we know that landers can be sent, and there's a group of of researchers who really want to send missions to Venus and land on the surface, but they don't seem to gain the right traction. With this most recent news from last year about this potential for phosphine in the atmosphere, I mean, it's still sort of contested, but it is of interest and people are listening. So I don't think it would be unreasonable for there to be a Venus lander in the coming years. But it is hard because they just don't survive. It's so unbearably hot.
There were 3, I think, successful Soviet landers. Yeah, it's very hot. It's a day and night. It's the same temperature. It's 460 Celsius or something. It's pretty hostile, as well as the atmospheric pressure, 90 times Earth's atmospheric pressure. But the problem is the heat. Your spacecraft heats up and the electronics fail. You don't survive very long on the surface.
Yeah, so you can generate the heat, but dissipating that
heat
is a problem.
You could have a balloon floating in the atmosphere at the right height.
And that is of great interest.
Where it's cool enough for water vapour,
yeah.
and there is water. Clouds are water vapour with a little bit of SO2 dissolved.
So it doesn't have to be that the end goal doesn't have to be on the surface. It can be in the atmosphere is actually a significant amount of the science that we're interested in.
That would be more reasonable.
Yeah.
I think we'd probably get a Mercury lander before a Venus lander, because at least on Mercury you can land at night. I mean, Mercury's 400 odd degrees by day. It's baking sun, unless you land at the poles, like we might do on the moon. But anywhere where the sun shines gets far too hot by day for a lander to survive. So what you do on Mercury is land round about sunset, operate throughout the Mercury night, and then expect the spacecraft to die soon after sunrise.
But Mercury night is a very long period of time, so you can achieve a lot.
Mercury night is quite long. It's well, the night is 88 Earth days,
which is
it's just 2 or 3 months worth of working time.
Yeah.
So you power yourself with a plutonium battery to work through the night, and then you die when you heat it up by day.
So still, I feel like we're often looking sort of outwards in the solar system, but there's actually still plenty more going on in the inner rocky planets.
Amy's asking, which is your favourite volcano in the solar system?
This is assuming I know many volcanoes in the solar system.
Well, it could be addressed to me.
I think you're going to have to answer
I'm reading these out because you haven't
I can't read them, yeah.
My favourite volcano actually is Kilauea in Hawaii. I've had some wonderful times there, and Hawaii is in the solar system. Yeah. It's nice. You can walk up to the volcanic rocks like this and see them with the wonderful textures on, see them glowing red hot, and it is a great thing to do. And the volcanoes in Hawaii are pretty good analogues for the bigger equivalents like Olympus Mons.
And also for lunar work as well. So some of the experiments that have been done in the past, which is looking at oxygen extraction from lunar rocks, they will go to fresh basaltic lava flows. So there have been some tests in Hawaii testing some of this technology, because you want really dry rocks, basaltic preferably. Yeah. They're really good analogue environments for places we want to go.
There's a long duration facility high on the slopes of Mauna Kea, yes, where they put people into a habitat and make them do simulated Martian missions. If you're going outside, you put a blooming spacesuit on before you go out and look at the rocks. Yeah, because a lot of it is about the sort of the psychological problems that come into play with these long duration crewed missions, and it's like how can humans survive in such isolation? It's not easy. People might think, get paid to stay in bed all day, but it's a lot more complicated than that. Well, we'll take this one more live question and then we'll look at the widgets and wrap up. Martin Hodnett is saying, with Mars in mind, would it be an idea to send a mission into a deep part of Valles Marineris, see if there was evidence of extinct black smokers lurking at the bottom? Okay, Valles Marineris is quite a deep feature. It's the big canyon system near Mars's equatorial region. If you could steer your landing, you've got a long amount of atmosphere to use your parachute to slow you down.
I'm just wondering, did Mars have its atmosphere and an environment suitable for life long enough for those things to develop?
Yeah, I don't think Valles Marineris is a black smoker type environment, because that black smokers is hydrothermal fluids interacting with hot rock. There may be some small volcanic fissures on the floor of Valles Marineris. They're not well characterized. I think there'd be other places to go to look for interesting features on Mars. The floor of Valles Marineris is going to be thickly covered in sediment now, so probably not a great place to go. I think these deltas, where we're landing at the moment, or the delta in Jezero Crater, is a very good choice of landing site.
It's trying to maximise all the different types of possible environments and things that you that could be of interest in a small area that a rover can go between.
Yeah, Amy's pointing out the Eridania Basin's been proposed as an area where hydrothermal activity may have occurred. Yeah, well, there are various such places, Amy. All right, Graham. Graham's saying, what's the frequency of impacts on the moon's surface and how safe is it to have a permanently manned base? Depends on size, doesn't it?
That's interesting, yes. So there are sort of models that tell us approximately how many meteorite strikes there are a year, but a lot of that includes as well some of like the really small ones that won't really, it's not hugely damaging to have these really micrometeorites, micron in size. But knowing that it is a concern, it's planned to build bases that will potentially be covered in the regolith or living in lava caves, for example, because this is all helping to protect against the radiation. I think the radiation is actually like the primary concern in terms of the environment, more so than the meteorites. And
this is all part of in situ resource utilisation, as well as living off the land, making your water. You armour your habitat in breeze blocks made of regolith if you can.
Just the regolith itself is a resource, and it's been used. People are looking at 3D printing to make roads, to make habitats and launch pads, and then extracting the materials and metals to make structures. So there's a lot there. A lot of the focus is on just getting crews alive and safe, and then we'll look more to sort of thriving and building colonies and whatnot.
Yeah, it'll happen one day. Okay, I think we need to wind up now. Thank you everybody for asking questions. Let's have a look at the widgets though before we finish. Okay, what's your first choice destination for the next lander? 76% say Europa.
And then the moon.
10% the moon, 7% each Mercury and Venus, and 0% Mars.
I guess people are they done with Mars? There's a lot going on Mars.
Well, I guess Mars is getting plenty of rovers anyway. Let's see what second choices are. Second choice, Venus wins.
Wow.
Okay, well, technology is no object or money. 43% say Venus. 23% second choice is Europa. They're presumably people who didn't have Europa as first choice. 18% the moon. 13% Mercury, and Mars still loses out.
I mean, it's great to see that. I know the focus is on Mars quite a lot of the time, but it's great to see that there is still a lot of interest in all of these other planetary bodies because there's just so much more to learn.
They're all interesting. We know far too little about them. Hannah, thank you very much for giving up your evening. Kate and Ben, thank you very much for running this for us as well. Thank you all for joining in. I will run another of these in November. Next year's S283 students will be invited. There's a Facebook group for current and past Moonsmoot people, so if you look for that on Facebook, you'll find out about the next event as well. And that's it. Thank you very much, and good night.